All right, we're going to get started today with the last part of chapter 6, and we'll probably start on to chapter 7 a little bit today as well. So the main topic for today is going to be stoichiometry of chemical reactions that occur in aqueous solutions. So in chapter 6, we've been describing the different types of reactions that occur, and then today we're going to talk about how to do stoichiometry within that context. So the book kind of covers stoichiometry really throughout the chapter, kind of interdisperses it throughout the different sections, but I think it's usually a little bit more efficient and effective to cover it all at once, which is why we're doing it now. So there are going to be a lot of homework questions that deal with stoichiometry. So after today, you should be well equipped to handle most of those. All right. So one thing I want to emphasize today is that what we're doing with stoichiometry today in the context of aqueous reactions is fundamentally no different than what we've already done all throughout chapter 5. The only difference now is that we're dealing with some different relationships involving moles. So whenever we do stoichiometry, as we talked about a lot in chapter 5, moles are going to be the key quantity. So typically the first step in any stoichiometry problem is to convert to moles. And that's because those coefficients that we have in the balanced equations can be thought of as molar ratios that allow us to convert the amount of one species, one reactant, or one product into an amount of another one. And that was, again, the whole major theme of chapter 5, but in that case, it was mostly dealing with mass to mole relationships. But now that we're in aqueous solutions, we did briefly introduce earlier this concept of molarity, which is a way of quantifying the concentration of a solution in terms of how many moles of solute are dissolved in 1 liter of that solution. So then we're going to use those relationships today in the context of stoichiometry. So if we're starting with a sodium chloride solution, let's say sodium chloride is one of our reactants that we're starting with, and we have 236 milliliters of the solution, and the molarity is 0.524 molars. Apparently they've moved on to some other activity besides thunderstorms, but I don't know what that is. All right, so how many moles of sodium chloride are in 236 milliliters of a 0.524 molar solution? So what we're going to use here is molarity is going to be often thought of as a conversion factor because this number here is 0.524 with a capital M. The definition of that is 0.524 moles of solute, which in this case is sodium chloride, per 1 liter of solution. So we have a ratio, a unit conversion factor now, that relates moles of solute to volume of solution. A common shortcut that I will take in this part, so I want to make sure I introduce it now, is that most often, not always, but most often when you're measuring volumes in the context of solution stoichiometry that we're going to be doing, milliliters is the much more common unit. A liter's a lot, so usually in a lab setting, you don't use a whole liter. So you could do the conversion in 2 steps where you convert liters to milliliters, or an easy way to do this is just to rewrite this conversion factor as the number of moles that you have, the molarity, but per 1,000 milliliters of solution. Because 1,000 milliliters, of course, is equivalent to 1 liter. So I will often write it in this way just to save 1 step and just write that as one conversion factor involving milliliters in the denominator instead of liters. You just have to remember, though, that molarity is per liter, so the denominator has to be 1,000 milliliters if you're doing it in that context. So then to answer the question that is posed here, if we want to find the moles of that reactant sodium chloride, if that's what it is, then we start with the given volume, 236 milliliters of the aqueous solution, and then we can use the conversion factor. And again, knowing whether we multiply or divide by the molarity comes from just unit analysis. So then we want milliliters to cancel, so we're going to have 1,000 milliliters in the denominator. So that milliliters cancels, and that's going to be 0.524 moles, the molarity, in the numerator. All right, so again, 0.524 moles per 1,000 milliliters. Milliliters cancels out. And that gives us then the moles of sodium chloride. All right, so then 0.124. So we're going to use that a lot, mostly as one of the steps in a longer set of conversions involving stoichiometry, but that key relationship using molarity to convert volume of solution into moles, or vice versa in some cases where we're going back into volume after calculating moles, that's going to be something that we see a lot. So then we can kind of expand the flow chart here that we already had built up in chapter 5. So again, just to remind you, in this flow chart, I'm going to just say A and B are two species in a chemical reaction. That can be two reactants, two products, one reactant, one product, just whatever role they're serving. Two different things that are involved in a chemical reaction. All right, so what we had already built up in the previous chapter, which is a good reminder now since that exam is coming up, is that we were primarily dealing with mass to mole relationships. So our previous stoichiometry problems usually took this form, where we were given the mass of A and we wanted to calculate the mass of B, or vice versa. And so then what we had to do in that case, as we said, moles is the key quantity. So we would go using molar masses to convert between mass and moles. And then the key stoichiometry part, which converts moles of one thing into moles of another, is where we use the reaction coefficients, the numbers out in front of each reactant and product in the balanced equation, which tell us the relative numbers of moles of each. And that allows us to calculate the moles of the other substance B, and then using its molar mass, we can go back into the mass. So that was mostly what we did in chapter 5. Now, chapter 5, we also introduced, now I have it sort of written out formally here, Avogadro's number, where we could actually go from moles into the number of particles of each reactant, particles being atoms or molecules, depending on what it's made up of. So we had Avogadro's number that we did with that, same for the other substance B. So all of this that I've written so far is stuff that we already covered back in the previous chapter. And mass to mass was the most common, but sometimes we ask you to calculate how many molecules of A, how many atoms of B, if it's an element, and so on. And the only thing we're really introducing now for chapter 6 in terms of solution stoichiometry is using molarity as a conversion factor involving moles, where that's going to relate to the volume of a aqueous solution of that species. So again, we have the volume of the solution. We can calculate number of moles using molarity, or go back in the other direction. And then same for the other one. If we have its molarity, if it's an aqueous solution, we can use that to calculate moles. So typically in the solution stoichiometry problem, volume of solution is your starting point, but you're still going to want to calculate moles as your first step, but this time using molarity as the conversion factor. Once you're in moles, you can go through any of these other steps, just like we did back in chapter 5. So sometimes you'll combine some of those concepts. So that's, again, emphasizing that what we're learning today is not entirely separate from what we've already done with stoichiometry. It just adds an additional layer to it. And I forgot to write this out, sorry. Got ahead of myself. All right, but anyway, these two here, the volume of aqueous solution related to moles by molarity, is really the only new thing that we have to add to our table. So you really want to think about the problems the same way, just recognizing now that if we're dealing with aqueous solutions and if we have the volume and molarity of those solutions, that's how we're going to be calculating moles. All right, so let's just do some example problems to see how this works. So this is going to be one where we actually combine two of the things that we learned. So we have molarity and volume of aqueous solutions here, but we're also going to then be using mass to mole relationships, because what we're ultimately looking for is the mass of the precipitate. So again, sometimes we do both things in the same problem. So if we're given a problem like this, just like any stoichiometry problem, if the chemical equation is not given to you, we do have to come up with it and write it out and balance it. It's a chemical equation that makes it more specific. So we're going to write out the chemical equation first. So this is a review of things we covered earlier in this chapter of determining chemical equations for precipitation reactions. So we know it's a precipitation reaction because we're asking you for the mass of precipitate, and we're dealing with two ionic compounds. That's the typical type of reaction those would undergo. So we have calcium chloride is one reactant. Silver nitrate is the second. And we just swap the cations and the anion. So calcium, which is the 2+ cation, is going to pair with nitrate, NO3-. So we're going to make calcium nitrate as one product. Correct formula for that is CaNO3 2. And then the second product is going to be silver chloride, Ag+, Cl-. So if we're writing out the chemical equation, specifically for this problem, because we're looking for the mass of precipitate, we have to identify which of the products would be the precipitate, which one's insoluble. So for that, we use solubility rules. Nitrate salts are always soluble. If you have NO3- as the anion, you don't have to think anymore. It's going to be in solution. But then silver chloride, silver is one that often forms precipitates unless it's with an anion like nitrate. There's a few other exceptions, but mostly silver compounds, especially the silver halides, are insoluble. So that's going to be our precipitate. So we identify that. Now, because this is a stoichiometry problem, we have to make sure we balance everything. So we can do it in different ways, but we can do it one ion at a time. We notice that this product here has two nitrate anions, but we only have one over here on the reactant side. So that needs a coefficient of 2. And if that gets a coefficient of 2, we now have two silvers as well, also two chlorides on the reactant side. So that coefficient will balance both of those. So coefficients are typically simple for ionic equations, but you do have to remember them. So that's going to be the full equation for us. Now, if we wanted to write the net ionic equation, that would just involve the two ions that are combining to form the precipitate, which can be written simply as Ag+, Cl-, making AgCl. I would say, though, in most cases for solution stoichiometry problems, this form of the equation here, the full sort of formula equation, is the most useful because usually that's how we're sort of given amounts of each reactant and things that are involved is in terms of the full ionic compound. So I would say if you're doing a stoichiometry problem, I would say don't bother with trying to find the net ionic equation. It's usually not going to help you at all. So I would say usually the formula, or what we call the molecular equation, the one that just writes out the full reactants and products like we did first, that's going to be the one that's most useful for you. Net ionic equations don't really help us very much in stoichiometry problems. You could use the net ionic equation, not like it wouldn't work, but there's really no, I think, real purpose to doing that. So it would just waste time coming up with a net ionic equation and not really benefit you at all in terms of solving the problem. So we'll just stick, for the most part, with these formula equations, particularly if we have to come up with it on our own, and like we did here. All right, so then we're ready to do the actual problem, which is to calculate the mass of silver chloride, which we identified as our precipitate, using everything we've been talking about today and earlier. So here's our equation again. And this form of the equation is perfectly fine for us. All right, so we're trying to find the mass of precipitate, which in this case is the silver chloride. So just like any stoichiometry problem, we write out what we're looking for first so we know when to stop doing conversions. And as is typically the case in a solution stoichiometry problem, molarity and volume is going to be our given quantities, and that's how we're going to calculate moles. So we'll start with the volume of the solution that we're given. And then we're going to use molarity to convert into moles. So just like we did in the one example problem earlier, we can write it as moles per 1,000 milliliters. So milliliters in the denominator so that the volume units cancel out. Molarity is 0.055, so that means there's 0.0555 moles of silver nitrate per 1,000 milliliters of solution, so that cancels out. Now that we have moles of one of our reactants, anything else we do with stoichiometry can follow exactly like what we've learned back in chapter 5. So we want to calculate the amount of silver chloride that forms. So we can now use mole ratios to do that. So we want moles of silver nitrate to cancel. We want to calculate how many moles of AgCl would be formed. We look at the coefficients for those. They're both 2. 2 moles of AgCl forming for every 2 moles of AgNO3 that reacts. So that was a trivial conversion there. And then finally, though, what we're looking for is the grams of AgCl. So if we want to convert moles into grams, we're back in that familiar relationship that we learned earlier of using molar masses. So we want moles of silver chloride to cancel out, and we want to find how many grams that corresponds to. So for that, we're going to use its molar mass, which is just the sum of the 2 atomic masses. So the molecular weight or molar mass of AgCl is just the 2 numbers added together, the atomic mass of silver plus the atomic mass of chlorine. If we go to the periodic table for that, Ag silver is number 47, 107.9 grams per mole. Chlorine is over here, number 17, 35.45 grams per mole. So we just need to add those 2 numbers together to get the molar mass of AgCl, just as a reminder of how we do that. So 107.9 is the atomic mass of silver, 35.45 is the atomic mass of chlorine, so that comes out to 143.4. Plenty of significant figures there for us. We don't need to go any more precise than that. So we're going to multiply by that. 143.4 grams of silver chloride in 1 mole. So moles cancel out like we want them to. We got 2 grams of silver chloride, which is what we're looking for. So we stop there and just do the multiplication and division, and we get 1.99 grams. All right. So really the only difference from this versus any other stoichiometry problem we've done is this first step here, using molarity and volume to calculate moles instead of the other relationships that we had previously developed. All right, any questions on that? All right, we'll do one more that's similar, and the only difference here is that we have to worry about limiting reactants. And again, the key question is, how do we know it's a limiting reactant problem if I didn't tell you in the title? Because what we see here is that we're combining solutions of 2 ionic compounds again. We're once again trying to find massive precipitate. So in a lot of ways, this problem is the same as the previous one, but we have now molarities and volumes of both reactants. So anytime you know the exact amounts of 2 or more of the reactants, you have to go through the steps to figure out which one's the limiting reactant to be able to solve the question correctly. In the previous problem, I just gave you the molarity and volume of one reactant, said how much precipitate can you form from that. Here, though, we have amounts of both reactants. We don't want to assume that they're in the exact right ratio, so we do need to go through the steps of determining limiting reactant. So this is going to have the same first step as the previous one. We do have to write out a balanced equation. Can't go anywhere without that. And as you'll see from doing the homework assignments, sometimes we're nicer to you and give you the balanced equation. Other times you have to come up with it yourself. So this is still a good review of other things that are important in this chapter of coming up with balanced equations for precipitation reactions. So we have 2 reactants here, sodium sulfide, lead nitrate, another nitrate compound again, very common for these types of problems. And they're going to react, and we just swap cations and anions. So the cation from the first reactant is sodium Na+, which is going to combine with nitrate NO3- to make our first product, sodium nitrate. And then our second product is going to be sulfide S2- combining with Pb2+ is the 2+ cations. There's 2 anions there that are -1. So it's just going to make a 1-to-1 compound, PbS, lead sulfide. Lead 2+, sulfur 2-, 1 of each to balance the charge. So that's the reactants and products. Now we have to figure out coefficients and which one is going to be our precipitate. So for coefficients, again, it's not usually too bad for these. You can look at it in a variety of ways, but we have 2 sodiums in this reactant. So we need 2 sodiums on the product side. And then I think that's the only coefficient we need in this case, because we have 1 lead 2+ on each side one sulfide on each side, two nitrates on each side. So we're done with just that one coefficient. Turns out in this problem, you don't even need this coefficient because it's not going to be involved in solving the problem, but that is the fully correct set of coefficients. Now we have to figure out which one is our precipitate. Sodium plus nitrate, those are two ions that are always soluble. So if you see either of those in the formula, you know that's going to be soluble, and we can just put an AQ next to it. But then lead, a lot like silver, tends to form insoluble compounds unless it's with one of those rare anions like nitrate. So lead sulfide would be insoluble based on our solubility rules. Most sulfide compounds are, most lead compounds are, and so pretty easy to identify that. So that's all we need then to know that this is our precipitate, and that's the only coefficient we have, which won't matter in the long run. Now, the only difference for this one from the previous one, though, is that because we have molarities and volumes of both reactants, we have to go through and figure out which our limiting reactant is. That's going to be our second step here. There's different ways of doing this, as we discussed back in chapter 5, but the way that I like to do it is calculate what's called a stoichiometric ratio, where we calculate the moles of each reactant and then divide it by their coefficient. Now, in this problem, both reactants have a coefficient of 1, so in reality, whichever one has the smaller number of moles will be our limiting reactant, although that's not always the case if you have coefficients other than 1, but here it's pretty simple. And we're going to calculate moles in the same way we've been covering today, which is using molarity and volume. So for the sodium sulfide solution, we have 125 milliliters. That's given to us in the problem. And its molarity is 0.250, so it's 0.250 moles in 1,000 milliliters of solution, or 1 liter is the more typical definition. We'll use that shortcut to get milliliters to cancel out and convert into moles. So we have 0.0312 moles of Na2S. And typically, as we said, you don't just stop at number of moles. You have to calculate the stoichiometric ratio to know if it's limiting reactant. So the stoichiometric ratio for that is that number divided by the coefficient. But the coefficient for sodium sulfide is just 1, so it's the same number. All right, so that you could have just done in your head, obviously. All right, so that's the stoichiometric ratio for sodium sulfide. We have to do the same thing for lead nitrate. Calculate the number of moles and then divide by the coefficient. This step is not a total waste of time because we do need the number of moles later on to start the stoichiometry problem, but we have to do it for both reactants in this case because there are 2 of them. So we have 95.0 milliliters of that solution. And then we have 0.450 is the molarity, so that's 0.5450 moles of that compound in 1,000 milliliters. So milliliters cancels out, and we end up with 0.0428 moles of that compound. I won't read the whole thing out. And then the stoichiometric ratio for that is just that number divided by the coefficient. Coefficient for lead nitrate is also 1. You don't need any coefficients on that to balance it, so it's the same number. All right, so once we calculate stoichiometric ratios, whichever number is smaller is our limiting reactant. So this one here, sodium sulfide, which has a stoichiometric ratio of 0.0312, that's going to be our limiting reactant. So whatever calculation we're asked to do now, which once again in this problem is calculating mass of precipitate, we're going to use the amount of sodium sulfide as our starting point because it's limiting reactant. It's going to determine how much of any product we have that would form. So we can go through then and do the calculations now, starting with the moles of sodium sulfide. Here I gave you the molar masses, so that's nice. I don't have to calculate it. So the last step here is just to do the calculations once we identify a limiting reactant. So we're looking for the mass of precipitate, which is lead sulfide in this case. Sodium sulfide is our limiting reactant. So we have 0.0312 moles of sodium sulfide. We just calculated that previously. We don't have to recalculate it. We just start with that number. And then we're going to use coefficients now to convert that into moles of the precipitate lead sulfide. Going back to our balanced equation, those two also both have coefficients of 1. Coefficient of 1 for lead sulfide, coefficient of 1 for sodium sulfide. So the one coefficient that we have doesn't even end up mattering. So we just have one of each. So it's a trivial conversion there. And then same final step is to use molar mass of lead sulfide to convert it into mass. So here we gave that to you as 239.3. So if you trust that number, you know that we can just use that to convert into grams. So we're looking for grams. So this is going to be our last step. Grams per mole is 239.3 in 1 mole. So moles cancels out. That gets us into grams. So we stop there and we get 7.47 gram. All right. So using molarity and volumes to calculate moles is the only new part of this. If you have the amounts of both, you still need to figure out what the limiting reactant is. That step doesn't go away. All right. So any questions on that? Okay, the next thing we're going to cover, and the last thing for this chapter, is sort of a variation on solution stoichiometry called titration. Now, for some reason, titration is a word that gives a lot of general chemistry students the heebie-jeebies, but it really is just a different way of thinking about solution stoichiometry. There's not anything really fundamentally different here. But let's talk a little bit about what the definition of titration is. Like, why do we use this fancy word to describe it? So what we're typically doing in a titration experiment is we're using a solution of known concentration. So we have one solution where we know the concentration. We're going to react it with another solution where we don't know the concentration, and we're going to use that information to calculate the unknown concentration. So we're using a solution of known concentration to determine an unknown concentration. So those two solutions then are going to react with each other in some way. Usually an acid-base reaction is most common, but there's other variations on this. So in a titration experiment, we mostly care about what the two reactants are and what their sort of ratio is that they react with each other. We don't care too much about what the products are, what their coefficients are. We're just looking at the amounts of two reactants that combine with each other and using that information to figure out usually the concentration, but there's other things that we can do with it, as we'll see. So the most common type is acid-base, where we're mixing a solution of acid and base, where one of them we know the concentration, the other we don't. So you can either add base to acid or acid to base. You can do it in either order. Usually the solution where you know the concentration is the one that you're going to be adding into the other one, but it doesn't have to be that way. So you mix those two things together until you get to what's called the equivalence or the endpoint. The equivalence point or endpoint, those two basically mean the same thing. So that's the point where, in an acid-base titration specifically, where the moles of hydroxide that you've added, or H plus, equals the moles of H plus or hydroxide, depending on what order you're doing the addition in, that were initially present. All right, so essentially what you're doing is you're starting out in a flask. This is what this sort of picture is showing. You're starting out in a flask with some amount of either acid or base down here. You don't really, again, you don't typically know how much there is. That's what you're trying to find out. And then you're adding a solution of known concentration to that. And the equivalence point is the point where however much OH minus hydroxide or H plus from the acid you had present, you've added exactly the right amount of the other reactant to balance that out. Now, how do you know when you get there? So typically the way we know that we get there is you either, the simplest way is to use an indicator. This would be some substance that changes color at the endpoint. We don't need to worry about all the technical details of that for this course, but you can see in this if you look closely, there's a little bit of a pink color in there. So that's your indicator. You'll kind of, if you've ever done a titration in the lab, you'll kind of, if you're using an indicator like this, you'll typically see a little bit of a flash of pink as the base is added to the acid. It'll kind of go away. And then at some point, once you've gotten to the endpoint, the pink color will persist, and that's how you know you've reached your endpoint. So usually colorimetric indicators like that are the most common. As you'll learn in more detail in the next course, Chem 2, you can also use the pH of the solution in acid-base titration to figure out where your endpoint is. But the simplest and the way that we really care about is with an indicator. But for this course, because we're a lecture course, what we mostly care about is how do we do the calculations related to this. So that's what we're going to mainly talk about. I wanted to introduce the concept of titration a little bit, just so you know what we're talking about experimentally. But obviously in this course, you won't be actually doing experiments. You'll just be doing calculations. So the calculations you're going to do are going to be things like this. So some of them are going to look just like stoichiometry problems, where we're just given an amount of one substance and trying to calculate the amount of another substance. And technically it's a titration problem, but really, again, it's just a stoichiometry situation that we're dealing with here. So here we're adding sodium hydroxide to 52.3 milliliters of this 0.297 molar sulfuric acid solution. We want to know how many milliliters of the sodium hydroxide solution are required. So it's just a stoichiometry problem, as I said. So we have sodium hydroxide, which is a base, NaOH, combining with sulfuric acid. And as we said, in any acid-base reaction, the products are going to be water and an ionic compound. I did not give myself enough room there. Okay. All right, so that's the reaction. Now, what we really care about in a problem like this, and in most titration problems, is the molar ratio that the two reactants combine in. So the products are water and sodium sulfate. You should know that for the sort of conceptual basis of this part of the course. But at the same time, we don't really need to know what they are, how many of them they're formed, because we care about the ratio of the two things that are reacting with each other in most titration problems. So to get those coefficients correct, what we should notice is that our base here only has one hydroxide in the formula, NaOH, but our acid has two hydrogens out front, H+. Remember that OH minus and H+ have to combine in equal ratio. So if we have two H pluses from the acid, we also need two OH minuses from the base. So that requires a coefficient of 2 out front of there. That also means that we're going to get a coefficient of 2 in front of water. But as I said, for a titration problem, we don't really care about that because we're not calculating how much water is forming. We're calculating how much of each of these two things reacts with each other. So the one that's critically important is that we get the ratio of those two correct. Anything on the product side for problems like this doesn't really matter. So now we're ready to do the problem, and we just set it up exactly like a stoichiometry problem. We write out what we're looking for, which is the milliliters of this solution, our sodium hydroxide solution. That's what we're trying to calculate. And then we just start with a given starting point. So typically in a problem like this, your starting point is going to be the substance where you know both the molarity and the volume, which, as we've already talked about today, allows us to calculate how many moles of that substance we have. So you always want to still calculate moles first. So you look for which substance do we know both molarity and volume. In this case, it's going to be sulfuric acid here. So we use the volume of sulfuric acid solution as our starting point, because we have also the molarity of that to get us into moles. So the molarity is 0.297, so that's 0.297 moles of sulfuric acid in 1,000 milliliters. Technically 1 liter, but this is a nice shortcut that we're going to use all the time. Once we're in moles of sulfuric acid, the next step in a stoichiometry problem is going to be figure out how many moles of the other substances that correspond to, the other substance here being NaOH that's reacting with it. So we use mole ratios now to convert moles of sulfuric acid into moles of NaOH. And so what we look at here are the coefficients, and we said that we needed a coefficient of 2 in front of NaOH to make sure we had equal numbers of hydroxide and H+, so we have a 2-to-1 ratio of those two. That's the step that a lot of people forget in problems like this. So make sure you're still balancing the equation and using the coefficients when you need to. And then finally, this last step here we haven't done yet, but we're looking not for the moles of NaOH, or not, in this case, the grams of NaOH. We're looking for the volume of the solution in milliliters. So we're actually going to go backwards and use now molarity again as a conversion factor to go from moles back into number of milliliters. So that's just the reverse of what we did in this first step here. We want moles to cancel out, so that has to go in the bottom now. And then we want milliliters of that solution to be in the top, because that's what we're trying to calculate. And then this molarity here, 0.126, tells us that there's 0.126 moles of sodium hydroxide per 1,000 milliliters. So we can use that, but this time we're going to divide by the molarity, 0.126 moles per 1,000 milliliters. That allows moles to cancel out. That gets us into volume of solution. So this last step here is just, again, the reverse of how we typically start these problems, going from moles back into molarity. Sorry, back into volume using the molarity. So we just have to calculate it out, and we get 247 milliliters. All right. All right. So any questions on that one? Still just stoichiometry, but using relationships between volume and molarity now twice in the same problem. Now that's one variation on problems that you might classify as being related to titration, but a more common situation and how we actually use titration in a lab setting is going to be demonstrated here. So what we typically do in a titration problem, as I said, usually it's used to determine unknown concentration, which is exactly what we're going to do here. But really at its core, what you're doing in a titration experiment is you're finding the number of moles of your unknown species where you don't know the amount of it. You find the number of moles, and then you're figuring out, what do I do with that number once I have it? Very often you're going to use the number of moles that you calculate to figure out the concentration of the solution in molarity, but there's other things you can do with that, other relationships that you can use once you know the number of moles of one of the reactants. So here, that's what we're going to do, and we're going to do that for a couple other problems as we move forward. So this problem here is also useful because it tells us the typical way that we figure out the concentration of an NaOH solution we're going to use in a titration experiment. As you might have learned if you took the lab course, this is just sort of trivia at this point for you guys, but sodium hydroxide tends to soak in a lot of water from the atmosphere. So when you weigh it out, you can't just accurately weigh out, this is how many grams of NaOH I have, and this is how many moles that corresponds to, because there's an unknown amount of water that's going to be soaked in by the sodium hydroxide. So if you want to actually know what's the concentration of your sodium hydroxide solution, since you can't just weigh out the substance and dissolve it and know that, this is how we typically do it. We're going to use a solid acid called KHP. We don't really need to know the formula of that, but it has one acidic proton, meaning one H plus in the formula. And so we're going to take 1.25 grams of KHP. That we can accurately weigh out and use it to determine the number of moles. So we have 1.25 grams of KHP, and then we just titrate it with sodium hydroxide until we get to the endpoint. And we measure that we need 56.3 milliliters of the sodium hydroxide solution to reach the endpoint. So we want to know what is the concentration then of that solution. So it comes out again from, we really still want to approach it like a stoichiometry problem, but this time, once we calculate the number of moles of NaOH, we're going to use that to figure out the molarity. So the balance equation is this. So we have KHP, which is our acid. We don't really need to know the formula of it, plus NaOH. And again, since we don't know the formula of the acid, we're going to form some salt. We don't really specify what that is, in water. But what we mostly care about is the ratio that these two things react in. So as we're told in the problem, this acid abbreviated as KHP has one acidic proton. NaOH has one OH minus in the formula. So these two things are going to react in a 1-to-1 ratio. That's all we need to know about them. We don't really care what the formulas are. We don't really care anything else except that they react in a 1-to-1 ratio. So that's the balanced equation. And then it's also always helpful to think about, what am I looking for before I start the problem, so you don't just start doing a bunch of pointless calculations. So what we're looking for here is the molarity of the NaOH solution. So the two things we need to calculate that are the moles of NaOH and the liters of solution. That's the definition of molarity. So we need those two things, those two numbers, to calculate what this problem is asking for. So the liters of solution is not directly given to us, but we know how many milliliters of sodium hydroxide solution we have. So that's going to be an easy conversion to get into liters. but we have to use stoichiometry to figure out how many moles of NaOH would actually be present. So we're going to start that part of it first to calculate the numerator. So we're looking for moles of NaOH, and that's where we're going to use the titration information to get there. So we're starting with 1.25 grams of our acid, which has this molar mass. I use this sort of fancy script M here, but that's just MW. That's how it would be more commonly written. So we're going to start with 1.25 grams of this acid that we abbreviate as KHP. That's not the actual formula. It's not potassium, hydrogen, phosphorus. It's just an abbreviation for it. It's not a formula. And then the molar mass of that is 2 to 4.22. So we can calculate moles of that substance because we have its molar mass. And that's 2 of 4.222. So 2 of 4.22 grams of that substance in 1 mole. And then we use the balanced equation to figure out how many moles of sodium hydroxide are required to react with that. So we have a 1-to-1 ratio here. So this last conversion is trivial, but there's 1 mole of NaOH for every 1 mole of KHP that's present. That's required to reach the endpoint. All right, so that gets us to moles of NaOH, and for this one, we're going to stop there. That's the number that we need. So we get 0.00612. All right, so that's the number we need for the numerator here. We got that, and then to get the denominator, it's just a conversion factor. We're looking for the liters of that solution if we want to calculate molarity. So we have 56.3 milliliters of solution that's given to us directly in the problem. That's how much is required to reach the endpoint. And we have 1 liter of that solution corresponds to 1,000 milliliters. So we just need to divide by 1,000 to get that into the right units. So 0.0563 liters. All right, so now we have the two numbers we need, and we just have to divide them to get molarity. Okay, so I gave myself another page here because we do need it. So the molarity then of the NaOH solution, that's the final number we're looking for, is the number of moles that we calculated, which is that number there, 0.00612. And the volume in liters, which is 0.0563. So if we forgot to convert that to liters, we would get the wrong number here, because molarity is always moles per liter. We don't cancel anything, sorry. It's just going to be those numbers divided, 0.109 capital M. Right? So titration problems, you often are going to be set up in this way where we have to calculate the moles of one of the reactants where we don't initially know the amount that we have, and then use that number in some way to calculate whatever number we're looking for, which in this case was molarity. All right, any questions on that? All right, just another example that's very similar in this case. So this time we have acetic acid solution with an unknown concentration, so that's the one that we don't know. We use 100.0 milliliters of the solution in the flask, and then we titrate with 0.125 molars of molar NaOH. We measure that 53.24 milliliters of the NaOH solution are required to reach the endpoint. So what is the concentration of acetic acid solution? Okay, so we're just very similar problem to the last one. We're looking for the molarity of our unknown solution, not unknown in identity, but unknown in concentration. So we just need those two numbers, the moles of that substance and the liters of that solution. All right, and as we said, typically the way this works is we have to use stoichiometry to calculate the moles to get that part of it. The volume is usually going to be given to us, but usually in the wrong unit. So we have here 100 milliliters of that. So we could probably do this one in our head. The volume of the solution in liters is just going to be 0.1. Yes, I left a zero out. That's enough. 100 0 liters. All right, so we have 0.100 liters. So that number we can get pretty easily if you can do that math in your head. That's just a unit conversion. So that's how much in volume we have of that solution. But we have to calculate the moles that are present using stoichiometry. So our acid, which is acetic acid, CH3COOH, is going to react with the base that we're adding, which is NaOH. We want to write out the full balanced equation. We make an ionic compound, which is the sodium cation with the acetate anion. So that's 1 plus 1 minus, so just a 1-to-1 compound. And then water. This one, again, has really no coefficients that we need to worry about, because one thing we have to remember with acetic acid, even though it has 4 hydrogens in the formula, only this one here that's bonded to oxygen is actually acidic, would actually react with OH minus. So we have 1 H plus, 1 OH minus, so they're going to react in a 1-to-1 ratio and then form 1 mole of each product. So there's no coefficients needed to balance this. That's the only acidic hydrogen that we have. So now we're ready to just do this problem exactly the same way as the previous one, where we calculate the moles of our acid using the information that we're given in the problem. So we start with the solution where we know the molarity and the volume, so we can calculate moles of that. So we have 53.24 milliliters of NaOH solution, and the molarity is 0.125 molar. So we can use that to figure out moles of NaOH per 1,000 milliliters. So that gives us the moles of one reactant. Now we can calculate the moles of the other using the coefficients. The coefficients are both 1, so this is a trivial step. 1 mole of acetic acid for every 1 mole of sodium hydroxide. All right, so when we calculate that across, we get 0.00666, ooh, bad number to choose in this if you're superstitious, moles of acetic acid. Okay, so that's the number of moles of acetic acid that we get. We plop that up here into our numerator to calculate molarity. And that comes out to, we just move the 0 over 1. That number there. All right, very similar to the last one. I guess the only key difference here is that instead of using the mass and molar mass of our known compound, which is sodium hydroxide, we're using its molarity and volume as our starting point. But it really just becomes a stoichiometry problem where we calculate the moles that way and then divide by the volume to get molarity. Any questions on those? Now, besides calculating molarity, there is a couple other things we can do with titration that you'll sometimes see. So one of those is to determine an unknown molar mass. So sometimes if you're trying to identify an unknown compound, we don't know the formula of that compound, getting the molar mass is sort of part of the equation to figure out what is this substance. And so you can do that with titration. So here what we have is 0.254 grams of an unknown amino acid. We'll just abbreviate it as HX, which means it has 1 acidic proton, and we dissolved it in water. The solution was titrated also with 0.125 molar NaOH, and we find that this time 27.1 milliliters are required to reach the equivalence point. What is the molar mass of the unknown amino acid? So this time we're looking for something different. We're not looking for a molarity of a solution. We're looking for the molar mass of one of the substances. So it's always good to, as a starting point, think about what is the definition, what is the equation that I use to calculate that quantity, and then find the information that we need. So we're looking for the molar mass or molecular weight of this HX unknown acid. So if you recall, the definition of molar mass or molecular weight that we introduced in the previous chapter is grams per mole. So if you want to calculate an unknown molar mass, the two quantities you need are the grams of that substance and the moles of that substance. So in this titration problem, we're still going to calculate the moles of our unknown, but we're going to use it in a different way. We're not going to use it to calculate a molarity. We're going to use it to calculate a molar mass using these two quantities and dividing them. The mass of our unknown is given to us in the problem. That's 0.254 grams. So the numerator we already have. We don't have to do any work to get that in this case. But we have to do stoichiometry to get the number here in the denominator, the moles of HX. So up top, I'll write out the balanced equation. Very simple again. Typical acid-base reaction where you form an ionic compound in water. Our acid has just one H in the formula, so we only need one OH minus to neutralize that, so it's going to still be a 1-to-1 ratio of those two. So no coefficients to worry about here. A lot of titration problems, that's going to be the case where the two reactants are 1-to-1, but don't always assume that's the case. Make sure you write out the equations to verify that. All right, but we're ready to go then. So we're looking for moles of HX so that we can get our denominator here and calculate it. So moles of HX, we start with the solution where we know both the molarity and the volume, which is sodium hydroxide. So we're using 27.1 milliliters of sodium hydroxide to reach the endpoint. The molarity of that solution is 0.125, once again, like the last problem. So we can calculate the number of moles of sodium hydroxide using the molarity. 0.125 moles per 1 liter or per 1,000 milliliters as a shortcut. All right, so that's moles of sodium hydroxide. What we need is the moles of the unknown. Once again, from the balanced equation, it's a 1-to-1, so there's no real math going here. It's just a simple conversion. 1 mole of HX is going to react with every 1 mole of NaOH that we have. Okay, so when we work that out, we get 0.00339 moles of HX. So then the last step is just to plug that number up here to calculate the molecular weight or the molar mass. So we have 0.254 grams is the amount of HX that we had that's given to us in the problem. The number of moles that we just calculated is 0.00339. So grams per mole is molar mass, so the number comes out to 74.9. All right, so that is another thing we can do with titration. Everything at its core is just finding out the number of moles that we have of one of the substances where we don't initially know that, and then just knowing what to do with that number once you have it. Here we use it in a slightly different way to calculate a molar mass. So we're going to see this same sort of definition and concept come up also in some future chapters, where if a problem asks you to find the molar mass of something, the two numbers you need are the mass in grams and the moles. So in some way, you need to get those two numbers, and you'll be able to get molar mass. So that's exactly what we did here. All right, questions on that? All right, so the last one here is showing us it's a lot more wordy of a problem, but not too much more difficult. That we can also do titrations with redox equations or any other type of aqueous reaction. Acid-base is the most common, but there are redox equations too, where you can set them as a titration. This one's pretty interesting because if we have permanganate as one of our reactants here, and it's going to be converted into manganese 2+. Permanganate has like a nice, also kind of like pinkish purple color, and so it actually serves as a self-indicator. It'll turn colorless when it converts into manganese 2+, but then once the reaction's done, any additional MnO4- you have is going to stay pink, and that's how you know that you're done. So it's a self-indicator. It's kind of cool that way. That's not important for this problem, though. But what we're talking about here is figuring out the mass percent of hydrogen peroxide that's present in hair bleach. I don't know if when I was in high school, like frosted tips and bleached hair were like pretty popular. I don't think that's true anymore, but people used to bleach their own hair all the time, and the active ingredient in that hair bleach is hydrogen peroxide. So what we're doing here is we're taking 14.8 grams of hair bleach, which is a solution that would have some amount of hydrogen peroxide and other inactive ingredients. And we use titration, and we're going to determine that 0.105 molar KMNO4 solution requires 43.2 milliliters. So we want to know what is the mass percent then of hydrogen peroxide that is in that solution. So it sounds like a lot here, but as a good starting point, let's look for what we need. We're looking for mass percent of H2O2. We haven't really talked about mass percents of solutions yet, but it is another way that we can sort of quantify the concentration in addition to molarity. But mass percent is still defined the same way. It's grams of that substance per grams of solution, which in this case is our hair bleach, multiplied by 100. So a mass percent of a solution is defined the same way. It's not as common to use as molarity, but it's just mass of solute divided by mass of solution multiplied by 100. Okay. So in this problem here, usually it's often common that one of these numbers is going to be given to us. So the grams of hair bleach, we're telling you that we're using 14.8 grams of it to do this experiment. So 14.8 grams of the solution, the hair bleach, but we need to figure out how many grams of hydrogen peroxide, H2O2, are present in there. That number we have to use stoichiometry to do. All right. Now, the only slightly tricky thing about this is that the problem is telling us that we're using KMnO4 solution, potassium permanganate, but then the equation is written in ionic form with just MnO4 minus. Don't get too confused by that because, again, basically K plus is just a spectator ion, so we're just leaving it out and writing the ionic equation here. But from the formula of this compound KMnO4, there's one MnO4 minus per mole of compound. So basically, however many moles of KMnO4 we have is equal to the number of moles of permanganate MnO4 minus that will be in that solution. So that's one thing just not to be tripped up by. But we can go through then and figure out what we're looking for, which is the grams of hydrogen peroxide using, again, just the information that we're given about the titration. So for KMnO4, we have 43.2 milliliters of the solution. And the molarity is 0.105. So we have 0.105 moles of potassium permanganate in 1,000 milliliters of the solution. That's what we're using to do the titration. And as I already said a little bit ago, not to be confused, our reaction here is written as in ionic form with just MnO4 minus. But because the formula of KMnO4 just has one potassium, one permanganate, when we dissolve that compound in water, we're going to get 1 mole. You don't have to do the step necessarily, but just to avoid any confusion, there's 1 mole of MnO4 minus for every mole of KMnO4 that we dissolve, just because of the formula of the compound only having one anion in the formula. Okay. So that's a trivial step that you don't necessarily have to do. But then what we're going to convert to is we're looking for the mass of hydrogen peroxide that would react with. So now it becomes a stoichiometry problem where we're going to use mole ratios to figure out how many moles of H2O2 that would react with. So from the balance equation, we gave it to you here. You didn't have to produce it or balance it. We have 5 moles of H2O2 required for every 2 moles of MnO4 minus. So it's a 5 to 2 mole ratio, 5 for H2O2, 2 for permanganate. So that gets us to moles of H2O2. Very often in titration problems, you would stop here because we would need that number. But what we actually need for this one is the mass of that substance to get the mass percent. So we have to do one more step, which is using the given molar mass, 34.02 up there, to calculate grams of H2O2 that would correspond to. So 34.02 grams of hydrogen peroxide per 1 mole. That's the molar mass of that substance. And so when we work all that across, we get 0.386 grams of hydrogen peroxide. So that's the number we're going to put up here in the numerator, 0.386 grams, multiplied by 100, and we get 2.61%. So 2.61% by mass of our hair bleach is hydrogen peroxide. So just showing you a few different variations, and always helpful in a titration problem to figure out what am I looking for and what numbers do I need to get that. And so if it's a molarity, you need moles and volume. If it's a molar mass, you need grams and moles. Here, you probably won't see this necessarily on exams, but we're looking for a mass percent, so you need the mass of both things that we're dealing with. So different variations, but if you kind of think about at the beginning, what do I need to solve this problem, that can guide you through what steps you would have to take to get there. Okay, any questions on that? All right, I think that's the end of chapter 6, so I'll try to mark it here. This is the end of exam 2 material. All right, so everything else that we covered today and on forward will be on the third exam or the final. So we're ready to transition then into chapter 7. Chapter 7 deals with energy that can be involved in physical or chemical processes. It's gonna the beginning of this chapter is gonna feel a lot more like a physics course than a chemistry course, but eventually we'll see how this all relates to chemistry. But let's start with some definitions that are related to this. So from the standpoint of chemistry, energy is sort of defined as the capacity to do work. So there's going to be two forms of energy, two limiting forms of energy that we could ever have. So there's kinetic energy and there's potential energy. Yes? Yes. You don't need to ask in the future. Feel free to go anytime you need to. Um, all right, so we have kinetic energy and potential energy are the two forms of energy that we would ever have. And that tells us how much, and then depending on how much of total energy that the system has is going to dictate how much work it can do on the surroundings. We'll get some more definitions related to that in a second. All right, so there's the kinetic energy can be sort of simply defined as energy due to motion. And then potential energy can be defined as energy due to the position, the location of something, or the composition of something. Now, in chemistry, really when we talk about energy in the context of a chemical reaction, potential energy is the one that sort of dominates, and that's the most important. Because anytime we have bonds between two atoms, as we talked about, there's a certain amount of energy that would be required to break those bonds, which means that there's that much energy stored in the bond. That's all classified as potential energy. It's energy due to composition, as I've kind of listed it here. Sometimes in processes that involve chemistry, you would convert potential energy into kinetic energy. So, like if you have a combustion engine where you're burning something and you're producing kinetic energy as a result of that, but really it all comes from, on the chemistry side, it all comes from the potential energy that was present. So whenever we're dealing with energy and sort of talking about how much energy does something have or how much energy is transferred between two things, we always have to define what's called the system and the surroundings. So the system is going to be the part of the universe that we are focusing on. So whenever we're measuring changes in energies, we don't typically measure absolute energy, like how much energy does this have? We're measuring often changes in energy as a process occurs. And so the system is the part of the universe we're focusing on when we make that observation. From the standpoint of chemistry, the system is usually an enclosed container of a substance. So if we're measuring some physical process on that substance that involves energy change, it would just be a closed container of that substance, or it could be, as we'll see later on in this chapter, a chemical reaction. So if we're measuring an energy change that occurs as a result of a chemical reaction, the system would be all of the reactants and products that are involved in that chemical reaction. The surroundings is everything else in the entire universe that's not part of the system. All right. So everything else that is not part of the system is classified as the surroundings. And as we'll see, typically when we're measuring changes in energy for a physical or chemical process, what we're going to be measuring is transfer of energy from the system to the surroundings. Now that might seem daunting because, like, well, The surroundings is the whole universe. So how do we actually measure how much energy is going into the surroundings? We play some tricks to sort of contain our surroundings into a much more useful form as opposed to trying to just let the energy go everywhere. So that's what we'll do. But surroundings, technically speaking, is everything else that's not part of your system. So these definitions are going to be abstract, but eventually we'll kind of come around to really understanding the practicality of it. So as we said, we don't typically measure how much energy something has. We measure energy that is transferred between system and surroundings as a result of some process that's occurring. And there's two ways to then transfer energy. So we said the actual energy itself that something possesses, if you want to think about it in those terms, is kinetic and potential. But then how is that energy transferred to something else? There's two ways to do that: heat and work. And so we're going to use, so whenever something transfers energy, it's going to have some change in energy, which is just the amount of energy it has at the end minus the amount that it starts with. And it's going to either gain or lose energy by either transferring heat between the system and the surroundings or by doing work on the surroundings or on the system. So heat is also known as thermal energy. And this is going to be the energy that's transferred as a result of a temperature difference between the system and the surroundings. And this one you've certainly encountered in your everyday life. You take a ice cube and drop it into a hot cup of coffee. The ice cube's not going to stay there forever because the heat from the hot water and the coffee is going to be transferred to the ice cube. And when does that heat transfer stop? It stops when the two things have reached the same temperature. Now, of course, in that case, the ice is going to melt and dissolve, so you won't really see it. But let's say you put, let's say you heat up a steel marble, a steel bearing on a hot fire, drop it in a cup of water. The water is going to warm up to some extent, and then once the water and the object reach the same temperature, that's when the heat transfer will stop. So anytime you have two things in contact with each other that have a different temperature, one would typically define as your system, the other is your surroundings. Those two things are going to transfer heat between them as a result of that temperature difference. And that's one way that energy can get transferred from one thing to another. The other way is called work. This is kind of an unsatisfying definition, but it's all other forms of energy transfer would be classified as work. This is when an object is being moved by a force. So when you're doing work on something, there typically is going to be motion involved. Whereas as a result of transferring the energy, the other thing's going to acquire some amount of kinetic energy and start moving. In the context of chemistry, both of these can happen, and we will talk about work in the context of gases that can either expand or can be compressed. That'll make more sense in chapter 8, but we're going to introduce a little bit here. But most things we do in a chemistry context, we're sort of restricting things to only have heat as the possible form of energy transfer, or to have work be so small that the heat dominates. And so mostly in chemistry, we measure energy transfer as a function of heat only, which is easier to measure, especially for reactions that happen in solution like we've been talking about. But work can occur, and we'll talk about that a little bit, especially at the beginning of this chapter. All right. So then when you have these two possibilities, if you're going to have then a change in energy, if your system is going to gain or lose energy, it's just a simple relationship then. The change in energy for the system is just the sum of Q, which is heat, and W, which is work. So if you know both of those things, those are the only two ways that energy can transfer. So if you know the value of Q and you know the value of W, you just add those two together. That gives you the total change in energy for your system. Now, what we want to make sure we understand before we start talking about how to calculate these two things is the sign convention, because Q and W and delta E as a result can both be either positive or negative. The system can gain energy, in which case delta E is positive, or it can lose energy, in which case it's negative, and Q and W can both individually be positive or negative. So let's talk about the sign conventions a little bit for this. So if heat is absorbed by the system, so if it warms up, if it becomes warmer in temperature, then Q would be a positive number. So whenever heat is absorbed by something, it's positive. So if we use that terminology. For work is going to be then positive if work is done on the system. So if I define this bag here as the system, if I'm lifting it, I'm doing work on it, then the work would be positive from the standpoint of the system. Okay. So work being done on something is a positive term. So if Q and W then are both positive, then of course delta E has to be positive. That means the internal energy of the system increases. All right. And then in the opposite extreme, if both of them are negative, so in order for heat to be negative, that means heat is released. So if your system loses heat, if it gives off heat and lowers its temperature during some process, that means the term for Q would be negative. And then if work is done by the system, a common situation for that would be if your system is a gas and then the gas expands and pushes up against a piston or something, then the system is doing work on the surroundings and then the work term will be negative. So if both Q and W are negative, delta E also then has to be negative, which means the internal energy of the system decreases. But it's also possible to have a situation occurring where the signs of Q and W are different from each other. So there's no restriction that whenever there's energy transfer between system and surroundings, that both Q and W have to have the same sign. Sometimes they can be opposite in sign. And in that case, delta E will be positive or negative depending on which of those two is bigger in magnitude. So if your heat is positive, meaning your system is absorbing heat, but your work is negative, meaning that work is being done by the system, whether delta E is positive or negative depends on which of these two numbers is bigger in magnitude, right? So delta E can be positive or negative. I don't need to write out the whole thing. Let's just say positive or negative, depending on which of those two terms is bigger. And then the opposite, of course, is also possible. You could have a situation where the system releases heat to the surroundings, but at the same time, work is being done on the system by the surroundings. So the two terms have opposite signs once again. This time, heat would be negative and work would be positive. So if that's the case, again, you're adding a positive and negative number, so that could be either positive, negative, or zero as your final result, depending on the magnitude of those two numbers. All right, so but the main thing of this is just to understand that when you look at problems that involve heat and work, this is the terminology you want to become familiar with that tells you the sign of Q and W, because sometimes we don't directly tell you that Q is a negative number, but if we say heat is released, a certain amount of heat is released, that tells us that the sign of Q has to be negative, and so on. So you need to become familiar with that to be able to understand the problems. Now, this is a part that kind of confuses people a little bit, but I have to introduce it a little bit. What is something that's classified as a state function? And what do we mean by path independence? So a state function from the standpoint of this course, an easy way to identify it is anything with delta in front of it. So if you see, we talked about delta E in the previous slide. If you see anything that has delta in front of it, delta E, we'll talk about one later on called delta H. Anything that starts with delta is classified as what's called a state function. Um, and then, so what that really means, what does it mean to be a state function? What's the significance of that? Delta always means final minus initial. So for any state function, the value of that only depends on where you start and where you end. Doesn't matter how you get there. So if we're talking about delta E, which is what we're starting with in this chapter, delta E is a state function and only depends on final initial states, not how you got there. There's going to be an infinite number of ways to get from one state to another, but the delta E just depends on those starting and ending points, not the path that you take to get there. That's what we mean by path independence. So as an example of how this works, this is just a totally random example to show you this a little bit. So let's say we have our initial state has an energy of 10 joules. Joules is the most common unit for energies that we'll see. And our final state has an energy of 20. Now we can easily tell that delta E in this case is 20 joules is our final, 10 joules is our initial, so our delta E is plus 10 joules. But the reality of the situation is we don't usually measure the absolute energy of the system. We measure energy transfer between systems and surroundings, and there's a whole infinite number of ways for us to get from here to here. So one way we could get there was, let's say we did 30 joules of work on the system. That would get us to a state where we have energy of 40 joules, but then at the same time we're losing 20 joules of heat. So delta E in this case would be Q plus W, which is plus 30 minus 20, still plus 10. So that's one way to get from our initial state to final state. But we could have done it a different way too. We could have initially lost 20 joules of heat, which would get us to negative 10 joules in terms of absolute energy. But then if at the same time we have plus 30 joules of work, and that's also plus 10 joules. So there's a whole infinite number of ways that we can get from our initial state to our final state where we would still get a delta E of plus 10, but there's different combinations of values for Q and W that would all be possible. So Q and W themselves are not state functions because the value of Q and the value of W depends on the path the system takes and exactly what's happening to get from point A to point B. But the delta E itself is a state function because it only depends on where you're starting, where you're ending for what that value would be. It's a little bit, it always blew my mind a little bit to think about that delta E is a state function, but it's actually a sum of two things that are not state functions, which was always wild to me. But that's the situation that we're in. Try to understand it as best you can. But we'll talk next time about how we actually calculate Q and W in different situations. So then get delta E and some other related things.